Yeah. Right. Thanks, Planeta. Yeah, so this is at the end of a workshop on quantum networks. So first I'd like to thank the organizers of that workshop, especially myself. But on a serious note, I'd like to thank Rafael, Planeta, for doing the lion's share of the organization of this workshop, and the IIP for letting us use their lovely institute. Yeah, so it's Friday, it's the afternoon, it's late, it's at the end of a workshop. So in order to keep people interested, I'm going to talk about things that don't exist, also known as general physical theories. Sometimes in the literature they're called general or generalized probabilistic theories. But like I said, they don't exist in general. We have two examples, which is classical physics and quantum physics. So I could just talk about computation of unicorns. And I can try and justify that. So, without further ado, let's start with the crazy big questions. Why quantum mechanics? Why did nature choose such a counterintuitive theory that really challenges most of our intuitions about physics, about the world, about nature, about everything? And so the first question is, well, what is counterintuitive about quantum mechanics? So compared to classical probabilistic theories, so statistical physics, Liouvillean mechanics, things like this, we get a range of phenomena, such as the Bell inequality violation, which we've heard a lot about this week, the expansion of classical keys using quantum systems without having to assume anything about computers, the fact that we have Shor's factoring algorithm, which is one of the great successes of quantum information, so we can factor numbers efficiently using quantum computers, and something a bit more technical, but it's a really nice stark contrast between quantum and classical. In communication complexity tasks, you can get an exponential separation between quantum and classical. And so in the past, I guess 15, 20 years, people have been asking, well, what if nature were to choose a different theory? Why does quantum mechanics have these features? And there's been a sustained effort to come up with theories that satisfy some fundamental physical axioms, such as that two space-like separated regions cannot signal to each other. So we want theories to be compatible with special relativity. However, the predictions of these theories is not compatible with quantum mechanics. So you can go back to 1995, the work of Pescu and Rawlich, where they explored the relationship between the violation of Bell inequality and special relativity. And then this was developed a bit later by Lucien Hardy into a more precise framework. And then there's further work done by John Barrett. But this is just a random sample of many papers along this line. Okay, so then if we go back to these features of quantum mechanics and we ask what's so special about quantum mechanics compared to these general theories that satisfy sensible axioms, well, you can exceed the quantum values of Bell inequalities using general theories. You can get larger violations. You can have theories which can also expand classical keys without having to resort to computational assumptions. The subject of my talk is going to be this one, so I'll go into detail about this one. And quite strikingly, for certain theories, you can get these tasks not only being exponentially separated, but also you can just trivialize these tasks using general theories. And these features of quantum mechanics and general theories have been shown to be related to this framework called device-independent information processing. And in this framework, we imagine that we have a set of devices, a set of boxes that take some inputs and produce some outputs. So these are just classical pointers and classical settings, so knobs on your box. And then you just get some statistics from these boxes in the form of PABC given X, Y, Z. So in a general framework, you have n parties instead of 3, but I just want to depict this. And it's a framework which is used in quantum cryptography very successfully. And the important assumption is when the parties are generating these statistics, they don't communicate to each other. Other than that, there aren't really many more assumptions are made about the device specification, like what's the mechanics of the device or what's going on inside the boxes. All the experimenters have access to are the correlations, these statistics on the right. And the nice thing about this simple setup is you can actually begin to characterize theories and the implications of having general theories. So depending on the theory allowed, we can actually have different sets of probability distributions. So for classical or local theories, you imagine there is some classical information lambda that's distributed to the parties ahead of time. And the probability of their outcome only depends on their choice of setting here and some lambda, which is maybe some classical computer program. So the statistics produced here are just equal to ones in classical theory are just these statistics here. So everything kind of behaves nice and locally, and maybe there are some correlations in the data that was distributed ahead of time. And in quantum mechanics, we have the instruction set. Instead of being lambda, we now have a density matrix, so we have some quantum state distributed ahead of time. And then the local operations are just measurements. They're just general measurements. But then going beyond classical and quantum, we can actually consider sets of statistics where we just don't want signaling to be exhibited in the statistics. So that means whatever the choice of measurement here or setting here, we don't want it to affect the statistics at another party. And the consequence of this is that all marginal probability distributions are well defined. So I can take the probability distribution of this, or these two parties, or all three parties, and each of them is well defined. And this just comes down to a bunch of linear constraints that when I sum over the outputs at one party here for a given choice of setting, if I change the setting, then the statistics are the same, and it just gives me this marginal distribution on these two guys here. Good. And from this, you get actually a really nice geometrical picture of what's going on. So the set of general non-signaling distributions is this nice, I kind of was going for the colors of the Brazilian flag, but it's come out a bit yellow. I wanted it to be a bit more green, whatever. So anyway, this is the set of non-signaling distributions. These are things which don't allow you to communicate arbitrarily fast across space and time. This is the set of quantum correlations, which is a bit of a beast to define. And these are the set of classical correlations. So this is all just living in some real vector space. And then given this nice abstract framework, we can study the cryptographic and communication power of quantum theory within this landscape of general theories. So we can ask, like, well, what's the consequence of, for some task of assuming this larger set rather than the quantum set? And in return, people have tried to use the consequences of information processing to somehow characterize the set of quantum correlations. So I mentioned earlier that general theories can really trivialize certain tasks, such as these communication complexity tasks. And so if you say as a principle, well, that just can't happen, you can't trivialize communication complexity, then this actually has nice consequences for the probability distribution that you could have in the laboratory. So that's quite nice. Okay, so that was a quick summary of device-independent, the device-independent framework. Now I have to just spend the rest of my time putting something there. So the connection between the device-independent approach and computation is really complicated. I know, because I spent some of my PhD thinking about it and got somewhere, but not really anywhere. No, it was great. It was brilliant. I had great papers. Wonderful. Go read them. So what I'm going to do is consider computation beyond quantum theory. So there is a literature about computation beyond quantum theory. So we've heard about computation with time travel, which in other words is closed time-like curves. So somehow you have a system that can travel backwards in time and you can do operations on this system. There's also quantum computation with post-selection. So that means if some event happens with some probability that's non-zero, you can just condition on that event and run some computer. You could imagine replacing the Schrödinger equation with some nonlinear expression. And then you get this thing here. And then, well, if you've heard of modal quantum theory, you can try and build computers from modal quantum theory. But the problem with each of these modifications of quantum theory, to try and think of a more general model, you start getting actually really ridiculous computational consequences. So for the first thing, you get something called p-space, which is huge, with a capital Y. And this was shown by Aronson and Watrous in 2009. With post-selection, you get something called PP, which again is really ridiculously powerful. This was shown by Aronson in 2005. For just nonlinear evolution, you can get things which are NP hard. And for this thing, you have some obscure complexity class, which I can assure you is powerful. So most modifications of looking at computation in theories beyond quantum theory, the modifications have been quite ad hoc and generally lead to a huge boost in computational power from just having standard quantum computers. So this led Scott Aronson to ask the question of whether quantum mechanics is somehow an island in theory space. So he said, to many physicists, however, quantum mechanics does seem like an island. Change any one aspect of the theory and the whole theory becomes inconsistent and nonsensical. So this also seems to happen for the case of computation. You change one little piece of the theory, and then you go from having a nice standard quantum computer to something ridiculously powerful. So this, by the way, Scott Aronson's a computer scientist, so I don't know how many physicists he spoke to, but maybe, hopefully that is the intuition of most physicists. Yeah, I guess. Yeah. Iceland's classical. Oh, okay. Oh, island, sorry. So now I'm thinking I've got classical physics and then quantum physics lives outside of this. Now I want to modify quantum physics somehow in some direction. So I'm thinking of embedding quantum physics in something more general. Now, does that theory itself live as an island in something vast? Theory space is the idea of theories more general than quantum theory, in which, say, quantum theory lives in. Well, I gave you I'm going to get onto that just to describe like a broad class of theories of which quantum theory is an example. Yeah, you can posit such theories, exactly. That's the idea. Yep. I mean, if you go back to, you know, this picture I had of the non-signaling in quantum and local distributions, that's like a particular feature of thinking of a more general theory than quantum theory. Except it's more general in the case of correlations it produces. I'll get onto it. So yeah, coming back to this issue, we saw that there are consistent ways of thinking about more general theories than quantum theory, and it doesn't lead to ridiculous consequences, just like for the case of considering correlations. So yeah, the main result of what we've been thinking about is there is actually a really nice methodical computational landscape of general physical theories that satisfy very sensible axioms, very sensible physical axioms. And then quantum theory nestles inside of that. And there's no reason to get ridiculous computational power outside quantum theory. So it's a nice framework in which you could think of theories a little bit more general than quantum theory. And you have a nice gradated way of thinking about computation. So the picture you should have in mind, really, is the takeaway picture, is this was for the case of correlations, for thinking about these Bell tests. So the most general theory was this non-signaling set of probability distributions. Now, for the case of computation, we have this big set here of all the possible computations allowed in these classes of sensible theories. And then quantum theory lives inside here, and then classical theory lives inside that. Except on the left, I was looking at correlations, so probability distributions. But now on the right, I'm thinking about computational complexity classes, which is one of our best ways of quantifying computation. Good. So in this talk, I'm going to introduce the broad framework of theories and then describe computation within these theories, talk about complexity classes, and hopefully you'll still be awake after that. And then I'm going to give a bound on these classes, and then give a computational model which saturates this bound. So you had that picture on the right, and I'm going to give a theory which gives you the most computational power. And then I'm going to say some other stuff and try and connect it back to the theme of the workshop, which is causal networks. Okay, so for this talk, it's really important that you're familiar with NP hardness, PP, P-space, BPP, BQP, sharp P, PH, X-space, NC, AMA to the promise BQP, stock MA, and so on. I'm going to mention like 5 more classes than that. So you should really have this picture in mind. Okay, so I'm only going to mention 4 complexity classes because to physicists, I think complexity classes are some horrible disease. And of these 4 complexity classes, it will turn out that 2 of them are a special case of the third, and this one I'm not going to define because it's actually quite obscure. But the point is, it exists. Okay, an important distinction, important thing to note here is that we don't actually know if all these classes are distinct, because basically in computational complexity theory, we don't really know anything. So it could be that all of these things are equal, or they're not equal. Basically, you can't really prove anything. But for the purpose of this talk, I'm going to assume that each of these things is this. I'm going to assume that at least some of them are distinct, unless I say otherwise. Okay, so the broad framework of theories I'm going to consider is due to Hardy, to Lucien Hardy, and to a group from Pavia, which is Giulio Chiribara, Mauro D'Ariano, and Paolo Perinotti. So these are examples of, yeah, so here are a couple of papers which, yeah, there are lots of papers in these frameworks, but here's a good sampling of the papers. Okay. So this apparently is what a laboratory looks like. Okay, good. So the idea is that systems can travel from one device to the next, so there's some connection between devices. And we can imagine on each device there is some classical pointer indicating a particular event that happened. So there could be just a single event, so something that happens deterministically, say, or there may be many possible events associated with every device. And given these devices, you can then just start coming up with a circuit framework. So you give a nice abstract representation of the circuits. So here we have some preparation and of a system. The system travels here. One of the systems travels here and another system travels here. There's some measurement made here. And there's some transformation on the system here and some measurement here. And given this nice abstract representation of general circuits, you can start wiring these things together and be a bit formal. So you say that systems are wires of a particular type. So this is just a labeling of the kind of systems you have. These classical indices are just the values of classical pointers, and they belong to some set. And you say that every closed circuit, so that means every wire terminates at a measurement, gives you a probability. And the idea is, given a theory, it should assign probabilities to these closed circuit events. And the nice thing is already it's operational because we're talking about probabilities. We have abstract objects, but they should give us probabilities. So we can imagine taking some of the probabilistic device, like a coin, and flipping the coin to decide which device we should use. So if we flip the coin and we get heads, then we plug in a particular preparation here. And if we get tails, we plug in a different kind of preparation. And then that should give us another probability, which is if the probability of heads is p, then the probability from the original circuit plus 1 minus p, the probability from the other circuit. But then the theory should be closed, and this should give us a third circuit with a preparation I, with a different preparation, with a different preparation here. So the idea that we should be able to add things together and get another thing in the theory. So that was very vague, but the idea is using this motivation to be able to mix between different transformations and devices, we can actually associate devices with real vector spaces. So we actually have a concrete mathematical underpinning of what's going on. And we can start putting in operational axioms. So one axiom is one of finite tomography. So for each device, there is a finite set of complement circuits. So I give you a device, and I'm allowed to plug any old device around it to get a probability. But there's actually a special set of devices that characterize the device completely. So in quantum theory, you can think of having a quantum state, and then you have a special set of measurements which give you tomography of the quantum system. And the nice thing is that you can just distinguish between devices by looking at statistics from applying the complement circuits. And mathematically, this implies a real vector space. And that the vector space of measurements is dual to the set of preparations. Good. So we can give a representation that preparations are associated with column vectors, transformations with matrices, and measurements with row vectors. And given this representation, we can impose tomographic locality, where every device can be fully characterized by just doing local fiducial circuits. So I've got some compound circuit here, and I don't need to do one big global operation, one big global circuit to that single device. I only need to do a set of local things. And by local, I mean associated with each wire. And a nice consequence of that is that the vector space is associated with devices with multiple wires, multiple types, is isomorphic to the tensor product of the vector space with individual types. So we have a real vector space, it can be made finite, and when I compose systems, I get the tensor product coming out from these operational axioms. And the nice consequence of this is that everything is really nice and linear. And we had a talk earlier in the week by Matty Hoban, he's over there, where he tried to get rid of some of the pathologies of closed time-like curves by having circuits which were linear. And we kind of get linearity for free. We don't have to kind of impose it. It kind of comes from free by considering convex combinations and having the probability distributions respect convex combinations. And if we have linearity, yeah. Yes, you can think, so you can go, so this column vector here, you can think of as a state of a system. It represents all the information. Yeah. 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 This P is the probability that the theory spits out. So when I compose these circuits, it spits out a probability. Yeah. Yeah. So I have my outcomes here. And so I prepare my state, some column vector, I apply my transformation, which is a matrix, and then I have my measurements here, which are local. The probability is, Well, yeah, I mean, yeah, but I'm saying like the underlying vector spaces themselves are linear. Taking the mod psi squared, yeah, okay, that's not a linear function, but yeah. Yeah, I mean, underlying everything is just essentially like linear operations. Yeah. Mm-hmm. Yeah. No. See, this is a row vector here now. So you can think of this as like a dot product here. So I have some vector, I apply a transformation to my column vector, I have a row vector, and I take the scalar product with it. And that gives me my probabilities. Yeah. 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 Okay, so in quantum mechanics, wires are just, the types are Hilbert spaces of particular finite dimension. The density matrices associated with preparations. POVMs are associated with the real vectors again. So everything can be embedded in real vector spaces. And then CP maps are just the transformations, which can again be written as matrices. And it's worth pointing out that quantum theory satisfies both finite tomography and tomographic locality. However, there are theories which are not quantum but satisfy these as well. Okay. So now I'll discuss computation. So the kind of computations we'll be considering are in the framework of decision problems. So the idea here is that you're given some input and you have to decide whether this input has a particular property. And then you output yes or no if it has that property or it doesn't. So given a number, you ask, is this number prime? It turns out this thing is can be done on a classical deterministic computer. And then you take sets of these decision problems, and that's essentially what a computational complexity class is. So if we think abstractly about what's going on, is we just give this input x, we then construct a computational device that should do the deciding for us. And the kind of device we should construct should dictate what kind of problems we can decide, right? If it's a very simple computer, then we shouldn't be able to decide very complicated decision problems. And we should really, because it's computer science, you have to do a lot of accounting. So you have to make sure you're not sneaking in any unwarranted powerful computation somewhere through the back door. So you really have to do very careful accountancy of what's going on when you construct this computational device. So this is how efficient computation should work. So the number of time steps in any computation should be bounded by some polynomial in the size of the input. This is the definition of efficient in theoretical computer science. So the polynomial could be n to the 4003, and that is still considered efficient. Okay, I'll just get that out of the way. Good. The construction of the computational device should be done efficiently, including the description of the construction. So what we have is we have some classical computer that runs in polynomial time steps, that given the input x, and some set of circuit components, then outputs a big circuit. So then we take all of these different elements and then plug them together in a particular way. We get some classical outputs from the classical pointers of the device. Then the classical computer comes along again and gives an output. Maybe it's yes, maybe it's no. So given all of the classical data from the circuit, the classical computer will output yes or no after polynomial time steps. So this thing is classical and efficient, this thing is classical and efficient, and because this thing is efficient, it should only ever give a description of what's going on, which is bounded in by some polynomial. Good. Was that okay? Was that I went through that quite quickly? Yeah. Yeah. Mm. Yeah. So the idea is, yeah, that exactly. So what circuit is constructed can depend on the input. Yeah. And then these classical pointers are just inherent in the device. So I have some gate set, which is just fixed from the outset. Each of these classical pointers is independent of the input. It's just, you can think of some, gate set in a quantum computer. And then you just look at the pointers. And then you're given your input X, the classical outputs from the computer. You do some processing, and then you decide yes or no. Okay, and now we can define a computational complexity class. Okay, there's a technicality. Yeah, there always is. So the idea is that these gate sets should also have an efficient description themselves. So, like I said, these are just matrices. They've got some real numbers in them. The description of these real numbers should be well approximated by some computable numbers, which can be computed in polynomial time. I think we've taken care of everything. We've accounted for all the possible ways in which bad computations can come in, but okay, we've done our accountancy. So now we've done that, we can actually say a decision problem is in the class BGP for a theory G if the probability of an efficient computation giving the correct output for a particular input is at least 2/3. So that means you're allowed to err with probability 1/3. So given the input, it can decide some property about the input, but it can get the answer wrong 1/3 of the time. And if G is quantum, then we get the complexity class BQP. Yeah. 2/3. It's not special. It just, it's a constant that they picked that's not a half. Yeah. You can have problems with a half, but yeah, so it's some constant bounded away from a half. So you can just basically take a half plus epsilon, where epsilon is some constant, and you can still have the same class, because you can amplify probabilities. Yeah. Sorry? Yeah. Yeah, it means any input, yeah. So just some abstract input X, yeah. So yeah, we get the quantum complexity class BQP if we have quantum, and we get classical if we have BPP. So if the theory is classical, then we get BPP. And yeah, I hate having to say PP all the time, but okay. So anyway, for all theories that I've described, we have this nice result from Lee and Barrett, two of my collaborators, where the computation in this theory is bounded by some obscure complexity class AWPP. Okay, it rolls off the tongue. But the point about this class is this is actually our best known bound on quantum computation. So, so if you think about this being the best bound on quantum computation for now, then we know that any theory satisfies this bound. Bound. This conclusions means the set of decision problems. So the set of problems like this is contained in the set of problems here. It's just a set inclusion. Okay, we actually have evidence that, sorry, this should say BQP, because this actually undermines the rest of my talk. So this should say BQP. So we have good evidence that BQP is not equal to AWPP. If you want to know, I can maybe sketch an argument, but I'm not so clear on it myself. Good. So we know that for any given theory, we have BGP, and it's contained in this larger set here. The natural question is, how tight is this? This bound? Just like we know that quantum theory satisfies no signaling, but there are theories beyond quantum theory. Is it a case that we know that quantum computation satisfies this inclusion? How tight is this inclusion? Well, it turns out that you can find a theory where you recover this bound. And the nice thing about this is the inspiration for this theory actually comes from the study of correlations. So if we go back to local correlations, we have something of this form, where you have some shared source and then a probability distribution over that source lambda. And we make the very, very, very sensible assumption that the distribution over this source lambda is positive and normalized. And, well, if you're a quantum optician, maybe this isn't so crazy, but if you think about relaxing the assumption of positivity for allowing quasi-probabilities, we actually have a really nice result. So I think this is kind of folklore in the study of non-locality, but this is a nice, recent, modern presentation of this result. And the theorem goes that a probability distribution is non-signaling if and only if there exists a quasi-probability distribution, Q, such that the probability distribution basically mimics the classical case, except we have this quasi-probability distribution. And it's worth pointing out that each of these probabilities is positive. So I should say there was some other work talking about entanglement witnesses, which basically has a similar structure to this. But this is like the most recent presentation I can think of. I think this basic result has been discovered many times. So I just picked this I picked the most recent reference I could think of, basically. Non-signaling was this, remember this, we had this larger region here. It was the one where you had these linear constraints that given that choice of input here, it doesn't affect the statistics of the other outputs here. Good. So the idea there from the case of correlations is you have a classical model, you have a low-code invariable theory, and then you bring in quasi-probabilities and you get what you want. You get the whole set of non-signaling distributions. You get the maximal set allowed. So what we're going to do is just basically mimic this idea. We're going to take a classical model of computation, throw in some negative probabilities, and actually get the most general theory that we want. So the classical model we start with is a probabilistic Turing machine. So Ariel talked about this. You talked about deterministic Turing machines earlier. So I won't spend too long on this, but the idea is you have some infinitely long tape and some machine that can read entries on the tape and it can write things to the tape. And it has some internal states. So a probabilistic Turing machine is something which also has a coin that it can flip. And then it uses the outcome of this coin to decide what to do next. So we have our initial step of the Turing machine with some state and some initial configuration of the tape. It flips a coin. If it gets heads, it goes to this step here with probability half, or it goes to this step here if it gets tails, and so on. And then the end of the computation, depending on the coin flips, it outputs either yes, yes, or no. So this probabilistic Turing machine outputs yes with probability 3/4. Does anyone want to do the math on that? Good. So a quasi-probabilistic Turing machine takes the probabilistic Turing machine and then just throws in quasi-probabilities. So we decided to call this an affine Turing machine because this is much easier to say than quasi-probabilistic Turing machine. And this machine has, instead of probabilities here, it's allowed to have rational quasi-probabilities. But we make a restriction that each step they sum to 1, just like in the normal probabilistic case. And then at the end, the sum of all the yes outcomes should give you some probability, should give you some positive number in the unit interval. So this is, so in the previous case, for the probabilistic Turing machine, you didn't have a minus sign there. So you flip a coin, oh, you tell me. I mean, if you think about a Wigner function in, say, quantum optics, I mean, that's like a quasi-probability distribution. There's like another example. You shouldn't think of it as something physical, just merely a mathematical object at this point. How do I think about negative probabilities? Well, I'm talking about fantasy theories, so, you know, I'm trying to intuit about things that don't exist. Yeah. So if this sums to 1, this sums to 1, I sum up everything here, I get 1. Well, at each stage I have negative probabilities. Yeah, but you can think of, like, there's the internal dynamics of what's going on inside the system, then an effective output of the system, which is either yes, 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 or no. Yeah? Yeah, so if you say this happened and this happened, you multiply the quasi-probabilities. Okay. So, oh, I'm going to avoid that question because you said the word entropy. What would be an entropy for this thing? That's a good question. We can tell me. But the nice thing about these affine Turing machines, they're a nice mathematical model that you can think about. And people have thought about this in the community, which we actually found out about after we started messing around with these things. And we could prove a nice theorem that a decision problem is in this mad class AWPP if and only if it can be decided by an efficient affine Turing machine. When I mean efficient, I just mean that the number of steps in the computation is bounded by some polynomial. Good. But the Turing machine is one particular model of computation, whereas my theory was talking about circuits. So it turns out in theoretical computer science, there are well-established techniques for going from your favorite Turing machine to a particular circuit. So in the case of deterministic, probabilistic, and quantum Turing machines, and vice versa. So there's a nice mapping between the two. So we can actually construct circuits from our affine Turing machines in the same fashion to get affine circuits. And the nice thing about this is we can build a causal theory from these circuits. So this just means that operations that happened somewhere in the past do not depend on operations that happened in the future. Okay, that's a picture of how you do the mapping between the two. I thought this might give you a hint of kind of how tedious it is to go through, but you can do it. But at this point I should say that the theory is actually a little bit pathological. It's not pathological in the same way that you kind of get crazy nonlinearities. It's pathological in the sense that it can give negative values, negative probabilities, if we compose circuits in very non-trivial ways. So if I just take two circuits and just have them in product form like this, I have probabilities coming out, which are nice and positive, and probabilities coming out here, which are nice and positive. Maybe we could, okay, maybe we postpone this discussion to the end, I think. Yeah. Is it all right if we postpone this to the end, maybe? Yes, exactly. Yeah, exactly. Yeah. Exactly. Yeah, it might be negative in between. Yeah. It's not a process, it's not a physical process, it's not something that's happening in nature, it's a mathematical model. Yeah. I'm saying there is some process going on. At the end, I have probabilities coming out. Well, I can't. I guess I don't think I'm going to make you happy. Yeah, exactly. You square it and you get something, but I'm not sure if that's what you want. I mean, you want me to tell you what a... Yeah. So anyway, I took two parallel circuits. They each give me probabilities at the end of the process. And then what I can do is rewire the circuits. So I can take this thing here because it has the same type as the thing going in here, and I can just hook them up together. Or I could just hook these two things up together. And it turns out in these affine circuits, I get negative probabilities coming out. But this is kind of like a normal theory should be able to be closed under such compositions, right? Because you just got this nice typing system. I should be able to divert some system here, put it in some other circuit, and take another one out. So the idea is that these affine circuits give a theory, but one where only very simple compositions are allowed. So this kind of has the feel of maybe like you have maps which are positive but not completely positive. So things break down under composition. Okay, so this outer limit, we have the theory of affine circuits, and we get back this weird complexity class AWPP. And then you could play the same trick for quantum, in the case of correlations, but now for computation, where I have the most general theory. Now, what principles are involved that get me back down to the set of quantum computations? So there's conjecture which goes back to this paper by Barrett in 2007, which can now be a bit more formally rephrased, which is that all theories allowing non-trivial composition can be efficiently simulated by a quantum computer. So our theory is ruled out because of this ability to swap wires gives you a negative probability, so it's not a closed theory. But somehow theories which allow this kind of composition should be able to be simulated by a quantum computer. And the motivation for this is that in quantum theory, there seems to exist some sort of trade-off between states and dynamics. You have entangled states, so you have very rich kinematics in the theory, but you also have entangling dynamics. Whereas in some other theories, you have states which have, say, more non-locality than quantum theory, but the dynamics in that theory is very limited. So that's the motivation for this conjecture. And we explored this in another paper. Okay. Right. So, yeah, there's a nice framework in which we can study computational general theories. From the physical point of view, there are some nice close analogies between the study of correlations and computation that we've exploited. And from a computer science point of view, an obscure complexity class that maybe has been a bit neglected has a surprisingly intuitive explanation in terms of these affine Turing machines. And it would be quite nice to have a killer application, and I think one application could be using these affine Turing machines to simulate quantum computation. And yeah, I'll leave it at that. Okay, do I have time to quickly mention causal networks? 5 minutes, okay. So there was a talk earlier about the triangle scenario, and we've heard about the triangle scenario a few times. The idea is you have an experiment where you have 3 preparations of systems which have 2 subsystems. And then you have some measurement device here, which is represented by the triangles. So there's just a single measurement made every time, and there's just some classical variable, which is an output. So you can look at the set of classical probabilities, P, A, B, C, produced in such an experiment, where now we have classical variables lambda, mu, and nu associated with each of the state preparations. And you have the probability distribution over mu, nu, and lambda, and then you have the probabilities depending on these things. And in the quantum case, you just have a natural generalization. We have a density matrix associated with P, Q, and R, and then measurements MA, MB, MC. And a nice observation made by Tobias Fritz was that you can't get this probability distribution with a probability half A, B, and C are all the same. And you can't get it with classical or quantum. And more generally, it's was shown by Henson-Laupuzzi that causal theories that are closed under composition, you also can't get this probability distribution for where the outputs are 0 and 1. And so a natural question now is taking our intuition from correlations, the Bell case, about being able to get all non-signaling distributions, and in the computation case, the ability to get all things in AWPP. We can ask, well, what do quasi-probabilities give you? Well, actually, I think this is a really nice open question that might help us give like a nice characterization of probabilities in this scenario, or more general causal network scenarios, without having to worry about particular quantum implementations. And a curious thing that should be noted is that actually complex probabilities, which at least I put the at least I put this. Okay. Actually reproduce this forbidden probability distribution. So it might be interesting that there's causal situations where our intuition really breaks down when we're thinking about quasi probabilities. Good. Okay. So this was based on joint work with John Barrett, Neil de Beaudra, who are both at Oxford, and Kiran Lee, who's now at UCL. And it may be on the archive at some point in the future, once we crack what negative probabilities mean. Good. Okay, one last thing. So the current workshop is the second in a series of 3 funded by FQXI. And we're very grateful for their funding, because it's made this possible. And the next one will be in Oxford in spring-summer 2017. The date is yet to be confirmed. We have like a potential list of invited speakers, but if you have any suggestions for speakers or format, whether you like this format and you would like it to be repeated, or maybe you want something a bit more intense and short, then please get in touch. And also, it'd be nice to keep this workshop going on beyond 2017. So if you're interested in discussing future venues for the workshop, then you should definitely get in touch. Yes, and also please come along, because in addition to invited speakers, we'll again be taking contributor talks and posters. Good. And with that, I finish.